This is a supplementary lecture on the net pressure force on a closed surface. So some of you may really not be interested in this, and that's fine. But for those of you who want to have some understanding for how this works, having a net force that points straight down on the wing, even if the shape of the wing is irregular, this is what we're going to be studying. You all know that on a regular closed surface, just sitting in a uniform pressure field, no matter what the shape is, that pressure is going to act in all directions on it, normal to the surface. Here's some atmospheric pressure. And it doesn't matter what the shape of the object is, it is not going to have a net force. And you know that because no matter what shape object you look at, whether it's this bottle, this ibuprofen, or this calculator, very different shapes, or this stapler, they don't just start moving when nothing's happening except pressure forces being exerted on them. So you already know that the net pressure force on a closed surface is zero if the pressure is uniform around that object. And what we're going to extend that to thinking about is, okay, but what if the pressure is not uniform? What if it's split on the top and the bottom, which is what we have in a wing situation. So in the wing situation, we typically have a pressure on the top surface of the wing that is different than the pressure on the bottom surface of the wing. So I've driven this isn't really even a wing. I've driven a blade here. It's got a length of L. It's got a width of W. It has no difference in shape. If you were to look at a side view of this, it's just a blade of width W. And this would be X and Y would be straight up. And so this has a net force on it acting from pressure. The top of the blade we say has pressure 1, so pressure 1 is on the top of the wing, and pressure 2 is on the bottom of the wing. And so if pressures 1 and 2 are different, you are going to have a net force. So, of course, there's nothing to cause that to be the case in this example. But nonetheless, if you had just a blade and it had different pressures, there would be a net force. You could easily calculate that. There is no net force in the X direction because there's no pressure is pushing only in Y. Pressure only exerts force normal to the surface. The surface in this case is facing the Y direction in both directions. It's facing positive and negative Y. So there's no X force simply because there is no pressure force in the X direction on this surface. In the Y direction, we would have an upward force coming from the bottom. So that's a positive component coming from P2 pushing up on the bottom of the blade. And from the top, we have P1 pushing down, which is going to cause a negative Y downward force. So our total net force for this non-wing would be P2 minus P1 times the area of the wing. The area of the wing, of course, is just L times W since it's just a flat surface. If we were to look only at the net force on the top half of the wing, it would be minus P1L times W. That is the pressure force on the top of the wing acting downward, pushing down on the top of the wing, whose area is L times W. So this is the key result. We're going to look at a lot of different top shapes now and see how this changes. So our F net top, if you actually put it in vector form, would be, we'll do it one more time just so we're very clear on this. The top vector force in X and Y coordinates, there's 0 X not top, and the Y, there is PLW. All right, so that's the result we're going to try to remember, and we're going to compare other shapes of wings to that. So these aren't going to be realistic wings, they're just going to be realistic shapes. The first one we're going to take a look at is a triangle. So let's imagine we now have a triangular wing. Looks like this. Still has the width W and the fundamental length L here. So it's not, the bottom area hasn't changed. So the bottom area is the same as it always was, but now the top area is changed, and certainly the top, orientation has changed. We have pressure 1 on this side, we have pressure 1 on this other side. We have to, give these guys some names so we can keep track of who is who. So I'm going to draw it a little bigger here so we can see it better, and I'm going to name them. I'm going to name this side the left side. So this is going to be left, and this is going to be right. I picked those names because they're on the left and the right, in case you were wondering. And then I have P1 acting on those surfaces, P1 acting normal to that surface, P1 acting normal to that surface. I still have P2 acting normal to the bottom, but the bottom hasn't changed. The bottom is just a flat surface LW. So there's nothing changing in terms of that. I'm going to give this angle an angle theta here. We'll say it's, both angles are the same for this example. Doesn't really matter what the angle is. I've drawn it as about 30 to 35 degrees, but it doesn't make any difference, as you'll see from a mathematical perspective. Our coordinates have remained this. X is going in that direction and Y is going upward. All right, so we're going to now try to calculate some stuff like the pressure forces. So I'm going to divide this in two. This is going to be L over 2 here, and of course L over 2 there. So E divided in half because it has theta on both sides. And we can easily see that if I label this dimension here, I'm going to put this again in again. This is going to be H. So this is going to be it's a new dimension that depends on theta and L over 2. The formula that you might remember, I hope you do, is that L over 2 is equal to H, which is the hypotenuse, cosine theta. So that's the formula, that's the definition of cosine. And so we can solve that for H, because in this case we know L over 2. So H is equal to L over 2 cosines of theta. So that's important. So we have the H is longer than it was, we'll see, in this case it looks longer because it's the hypotenuse, right? So it's going to be longer. So that's our H. Now if we want to calculate the force, the total force on this surface, we have to calculate the magnitude of that force. So the magnitude of the force on the left side, that stands for magnitude, is going to be the pressure 1 times the width times H, which is equal to pressure 1 times the width times the length divided by 2 cosines of theta. So that's our magnitude of force on the left. The magnitude of force on the right is going to be the same, and I hope you see that. It's the same length H, and so magnitude will be the same. So we have the same magnitude on the left and the right. So it's also P1 WL over 2 cosine theta. So that's pretty simple. Now we're going to try to relate that to Fx and Fy. So we can turn this into a proper force vector. So if this is theta and this is my magnitude of F, remember it's pointing normal to the surface. So this is F left, pointing right into that surface at a normal angle here. And I can break that into Fx and Fy, and this is going to be theta here. So if this is theta here, that angle will be theta. How do I know that? Because this angle is going to go to 90 degrees if this angle is going to go to 90 degrees, and this angle is going to go to 0 if this angle goes to 0. So that's how I remember which is which. So there we have that. So this is going to be right here is F Y left, right? And this here is F Y right. Not left, sorry. F is the X right. You just said that wrong, stupid. F X left. Perfect. I said it perfectly backwards. All right, blow that up, dummy. So we have the magnitude here is F left. I've got theta here. This is F Y left. And this is F X left. All right. So now we can come up with terms for those because we know trig. So F Y left is going to equal the magnitude of F left times cosine theta. And it's going to be negative because it's pointing in the negative y direction. F X left, this one, is the magnitude of F left times sine of theta. All right, so now I can write these down for all of them. So I'm going to go ahead and write all 4 of the forces. So I have F left y minus magnitude, this is the one we just did, of F left times cosine theta. But that's equal to minus P1WL over 2 cosine theta times cosine theta. Now I've plugged in my magnitude of F left there. So my F left x is equal to magnitude of F left times the sine of theta, which is P1 WL over 2 cosine theta times the sine of theta. F right y is equal to minus F right magnitude times cosine of theta, which is equal to minus P1 WL over 2 cosine theta, because the magnitude of F right and F left are the same in this case because they are identical. The two sides are identical because the shape is symmetric. So F right and F left magnitude are identical. What's different is the direction. So if you look at the right side, it's going to point this way, which means it's going to have a downward y component, which it does, a negative y component, and it's going to have also a negative x component, whereas this one had a negative y component and a positive x component. So F right x is going to be negative F right times the sine of theta, which is equal to negative P1 WL 2 cosine theta sine of theta. All right, so those are my 4 components. I have an x component and a y component for both this surface and this surface. And now I can add those all up to get my F net top. So here's my net force that's exerted by pressure on the top surface. So obviously it's F left x plus F right x, and the second entry in the vector, F left y, F right y. And I have terms for all of those. I have F left x, I have P1 WL over 2 cosine theta sine theta, and then minus plus F right x, but F right x here has a negative sign, so negative P1 WL over 2 cosine theta sine theta. And then for the y component, I have F left y, negative P1 WL over 2 cosine theta, and then I have F right y, which is also negative P1 WL over 2 cosine theta. You can see that these are all in parentheses, as a vector. You can see that these two are the same. They're just going to cancel each other. These two are going to add together, but the cosines cancel out in both terms. So my F net top for this shape of wing, this weird wing shaped like a triangle, is 0 in the x direction, and in the y direction, it's just minus P1 WL divided by 2 plus P1 divided by 2 is just 1. So it's just this. So it's the same. So changing the wing from a flat blade to a triangle shape didn't change the net top force. It's the same as what we had when we just had a blade. So the F net top for the blade was 0 P1LW and negative P1L, and now it's also negative P1WL. So those are exactly the same. So that you could say is, all right, that proves what? Doesn't prove anything actually, it demonstrates. It demonstrates that that net force is not sensitive to the shape of the blade, at least provided that the blade is symmetrical. But what if this wing shape is not symmetrical? So we'll do one more example for those of you that are done, totally understandable. But I'm going to do one more example because you could be wondering if this still works when it's asymmetric. So we're going to take an asymmetric example, very simple one, but nonetheless very clearly asymmetric. Here's my wing now, another stupid triangle wing. But in this case, I've got theta here, it doesn't matter what theta is. So that's my new wing. So L is the same, W is the same, so the bottom of the wing is the same, still LW in the bottom. But now the top, of course, is going to be different. We're still going to have, P2 on the bottom, if you want to think of it that way, and P1 on the top. So the top is both here and here, right? So we're having pressures facing the top pressure affecting both of those sides. I have to give these names that I can keep track of, so I'm going to call them HL and HR. So this one will be HL, this one will be HR. This, of course, is still just L. I can see that HL times cosine theta is going to equal big L. So I can get HL is equal to L over cosine theta. Similarly, HR is equal to HL sine of theta. So HL sine of theta, sorry, theta's here. Sine of theta gives you HR. Well, but I know HL, so I can say HR is equal to L over cosine theta sine of theta, which is equal to the tangent of theta times L. So those are my HR and my HL expressions. So I can go ahead and calculate my pressures. That the magnitude of the left-hand force is equal to P1 HLW, and the magnitude of the right-hand force is equal to P1 HRW. And we want to be able to sort of see how that's going to translate into X and Y forces here. So we've got the left-hand force coming in this way. So we're going to have an X and a Y component of that based on theta here. There's your theta, there's your theta. So this is going to be your Y component of that. It's going to be your X component of the left-hand force. So there's your FL. But on the right-hand force, it's pointing in the absolutely negative X direction. So there's no Y component to that at all. There's only an X component. So we're going to, write all those down. So your F left Y force is equal to the magnitude of F left times cosine of theta. And it's negative because it's pointing in the negative Y direction. The F left X force is equal to the magnitude of F on the left, again, times the sine of theta, and it is pointed in the positive X direction. So we have a positive force coming from that in the X direction. In the right side, FRY is equal to 0. There is no component of the right-hand force that goes in the Y direction. But F right X is equal to the magnitude of FR. So it's the total force in the right side is pointing in the negative X direction. So I put a minus sign there. All right, well, we already had we have our HRs and our HFs. We have our HLs and our HRs, so we can plug in for these magnitudes. So we'll do that, and let's do that now. So that's going to be here. You're going to plug in that FL is going to be minus P1 HLW cosine theta. And this one's going to be FLX is also with FL, so P1 HLW sine of theta. And then this is, of course, 0. And this is FR, which is P1 HRW. All right, so those are our forces. We know HR and HL. We'll plug those in next, but let's first write them all down here. So we have F net for the top is equal to those X components. So we've got two X components. We've got F left, which is P1 HLW sine of theta minus, sorry, that should be minus sign, minus the right-hand component, which is minus P1 H right W. And then we've got in the y direction, we have got only one component because there is no right-hand y component. So we have minus P1 HLW cosine theta. Now we just need to plug in for HL and HR for our final result here. So go in here, I'm going to plug in HL and HR. So F, this is a vector, F net top is equal to L over cosine theta, which is my HL, times P1 W sine of theta, minus, sorry, that's a minus sign, minus tan theta L times WP1, where I've replaced this is my HR and this is my HL. And then in the second term, I have minus P1, I have HL again, so L over cosine theta times W cosine theta. All right, so that's that. So your F net top is equal to this top term, that's a tangent, sine over cosine. So I've got tangent theta LWP1 minus tangent theta LWP1. And in the bottom, cosines cancel. I've got minus P1LW. So the final answer for the net top force is equal to 0 minus P1LW. So it is the same again. So we find once again that even with an asymmetrical shape of this triangle that's very lopsided, the net force from a pressure on that closed surface is just the top pressure times the area normal to the direction of interest, to the negative y direction, to the y direction, because all the x forces on that closed surface, no matter what the shape are, if the difference is here, all the net x forces are going to just cancel each other. The only forces that matter are going to be non-canceled are the ones pointing straight down. So that if P1 is different than P2, that's why it's being split in this direction, up and down, then you're going to see only force that's going to be relevant is the downward force from this top surface, and the downward force is going to be equal to P1 times the cross-sectional area of this. That is, does not matter what the weird shape is. It only matters what the area is in the direction perpendicular to the y direction here.